like, comment, share and subscribe. And if you have any question, then you can ask your question in the comment box. Good morning friends. Today we will discuss about the histology of ovary and follicular development. The histological appearance of the organs that compose of the female reproductive system undergo cyclical structural changes that are not pathological. These organs include the ovary and uterus, and the histological changes in these organs are being largely by four forms: follicle stimulating hormone, luteinizing hormone, estrogens and progesterone. Here I will describe the histological changes in the ovary throughout the course of the menstrual cycle. The first is the ovary. The human ovary consists of an inner medulla and outer cortex with indistinct boundaries. The medulla contains the blood vessels and nerves, whereas the cortex is occupied by developing follicles. A cross section of an ovary will reveal follicles in various stages of development. The next is the primordial follicle. An ovarian follicle progresses through several distinct phases before it releases its ovum. During the first 5 months of development, a finite number of primordial follicles form in the fetal ovary. These follicles consist of oocytes surrounded by a single layer of squamous follicular cells. These primordial follicles remain in the process of the first meiotic division. At the puberty, they begin to develop further and become primary follicle. The early primary follicle. At the start of each menstrual cycle, a limited number of primordial follicles are triggered to develop. The first apparent histological state is the early primary follicle that consists of a central oocyte surrounded by a single layer of follicular cells, which have been cuboidal. The zona pellucida is a thin band of glycoproteins. It separates the oocyte and follicular cells. Proteins on the surface of sperm will bind to specific glycoproteins in the zona. The late primary follicle. The late primary follicle, it is a stage in which it is reached when the follicular cells proliferate into a stratified epithelium known as the zona granulosa. The zona pellucida enlarges and can be seen even more clearly in the image which I will show you. The next is secondary follicle. The characteristic feature that distinguishes secondary from primary follicles is the appearance of a follicular antrum within the granulosa layer. The antrum contains fluid which is rich in hyaluronan and proteoglycans. The increase in cell layers of the zona granulosa, the thicker zona pellucida and larger oocyte. At this stage, a layer of cells outside the follicle become evident. These cells compose the theca interna and contribute to the production of estrogen. Just recall that the production of estrogen requires both the cells of the theca interna and granulosa cells. Estrogens, like all steroid hormones, are produced from cholesterol through a multi-step process that requires several different enzymes. Neither the cells of the theca interna nor the granulosa cells contain all of the enzymes necessary to convert cholesterol into estrogens. Theca cells contains enzymes that catalyzes the initial conversion of cholesterol into androgens, but it lacks aromatase that carries out the final step of converting androgens into estrogens. Consequently, androgens produced by theca cells diffuses into the granulosa cells, which contains aromatase, but it lacks the enzyme for the initial steps in estrogen synthesis. The theca cells are a better position to catalyze the initial steps in estrogen synthesis because they are closer to blood vessels and they can take up LDL to obtain cholesterol. The next is graphene follicle. It is the stage after the first meiotic division has completed but before ovulation. The oocyte is now a 2N haploid. The follicle is characterized by a large follicular antrum that makes up most of the follicle. The secondary oocyte, having undergone the first meiotic division, is located eccentrically It is surrounded by the zona pellucida and a layer of several cells known as the corona radiata. When released from the Graafian follicle and into the oviduct, the ovum will consist of three structures: oocyte, zona pellucida, and corona radiata. Corpus luteum. After release of the ovum, the remaining cells of the granulosa and theca interna form the corpus luteum. The center contains the remains of the blood clot that formed after ovulation. Surrounding the clot are granulosa lutein cells, and on the outside theca lutein cells. These cells these cells produce progesterone and to a lesser extent cholesterol. The granulosa lutein cells have an appearance characteristic of steroid producing cells with pale cytoplasm indicating the presence of lipid droplets. Theca lutein cells are smaller and are deeply stained. Blood vessels penetrate into the region of the granulosa lutein cells, allowing them to take up cholesterol to be used to synthesize progesterone. The activity of the cells of the corpus luteum is being sustained by luteinizing hormone. If the ovum is fertilized and implants in the uterine wall, human chorionic gonadotrophin, that is HCG, replaces LH to sustain the activity of the cells in the corpus luteum. The next is corpus albicans. If fertilization doesn't occur, the cells of the corpus luteum remain active for roughly 14 days until the levels of LH fall, and the corpus luteum involutes to form the corpus albicans. The secretory cells of the corpus luteum degenerate, are phagocytosed by macrophages and replaced by fibrous material. The last one is the atretic follicle. Each menstrual cycle, several primordial follicles are being stimulated to continue development, but only one follicle completes development to release an ovum. The other follicles degenerate through a process called atresia, which can occur at any stage of development. During atresia, granulosa cells undergo apoptosis and are replaced by fibrous materials. The oocyte degenerates and the basement that separated the oocyte from granulosa cells thickens to become the glassy membrane.